So I have been working on this topic now for quite some time. So I thought it's a good idea to give this talk in this software center seminar. So let's see the outline of today's talk. First, I will give a gentle introduction about this control dependency, and then we will see the most general definitions of control dependency that is being used nowadays. And then afterwards I will show two examples of client analysis that uses control dependencies. One is program slicing and another is timing leak or cache attack. Then I am extending this idea now to extend these concepts for time sensitive weak and strong control closure, which are kind of control dependencies that takes into account the time informations to detect timing leak or cache attacks. So, and I will give a hint of how to compute this weak control closure. Finally, I will discuss the results, contributions, and future work. So what is control dependency? It is a relation between two program statements stating whether one controls the execution of another. If we consider this simple code fragment, this condition in the while loop controls the execution of this update instruction x at statement 3, and then we say that statement 3 is control dependent on statement 2. A very related term that often comes in pair with control dependency is data dependencies, which is also a relation between two program instructions, stating that one instruction defines a variable that is being used by the other instructions. For example, the use of x at statement 4, this use of x is being defined either in statement 3 or in statement 1, and then we say that 4 is dependent on statement 3 or statement 1. So this kind of control dependency or data dependencies are encoded in a graph called program dependency graph, in which each node in this graph represents program instructions and the edges represents either data dependency or control dependency. And there are many uses of this program dependency graph, from program optimization, program debugging, bug detections, program parallelizations, software testing, etc. So this is the standard definition of control dependencies, but this definition is very informal, and this definition is hard to work with very large unstructured programs. So there is a formal definition of control dependency, which is usually provided at the level of the control flow graph. And in the control flow graph, each node in this graph represents program instructions, and the edges represents flow of execution execution of the of the instructions states. Anyway, the definition of formal definition of control dependency is like this: a control flow graph node M is control dependent on another control flow graph node N if N determines the execution of M in the following way. For example, every node between N and M must pass through M to reach the N node, and in that case we say that M post dominates N. This is the first condition that have to be fulfilled, and the second condition says that N can reach the exit node without going through M. Then we say that M does not strictly post dominate N. If these two criteria are fulfilled, then we say that a control flow graph node M is control dependent on control flow graph node N. And we see that this definition relies on the existence of the unique N node or unique exit node of the program. But this is a formal definition, and we can use it to compute control dependencies from many different kinds of programs. But there are some limitations of these definitions. First of all, the program must have a unique exit point. This is the first limitations. But we have modern programs that contains, for example, exceptions that leads to multiple exit point of the programs. So this definition will not work there. Another limitation is that this works only for terminating programs because there must have an exit point. But non-terminating programs are very common nowadays. For example, non-terminating reactive systems or distributed systems or even robot control software where the program never terminates. And so this definition will not be suitable for this kind of software. And also this definition is intra-procedural. That means it does not take into account the context of inter-procedural programs. This is another limitations. And finally, this definition is very much syntactic in nature, means that this definition works on the control flow graph structure of the program. But client applications exist that require considering the semantics of the program. For example, slicing probabilistic programs, we may need to take into account the program semantics there. So these are some limitations. We will not consider all the limitations, but we will see that there are better definitions of control dependencies. Two such concepts are called weak control closure and strong control closures. These are the most general definitions of control dependencies in the sense that numerous definitions that are introduced in the literature by other authors. These definitions are the special cases of control dependencies captured by weak and strong control closures. So let's start with the weak control closure definition. It captures basically non-termination insensitive control dependencies. That means the programs, if there exists any non-termination in the code, this definition does not take that into account, and it treats all non-terminating execution as terminating execution. So this definition is non-termination insensitive. And the definition is like this: given a subset of V of control flow graph nodes, this V it can come from the client application of this weak control closure. So we are given any subset V, and we say that V is weakly control closed when if for all control flow graph nodes n which is not in V, two conditions must satisfy. If n is reachable from V, then all control flow graph paths from n ending at a node in V must meet at a unique node. So I will explain this in this graph. For example, suppose V includes this node N3. So if we consider node N1, we see that the paths from N1 to N3, all the paths, they must meet at N3. And no other node should be from V in these paths. Then we call them V paths. And if we have unique V paths here from any node like N1 here, then we say that N1 is weakly deciding in this case. No, N1 is not weakly deciding in this case, and then V is weakly control closed. So I will use a pen here. This is a difficult concept to explain, but so for example, suppose we have a start node here. This start node is in V, and this N3 is in V, and this definition says that if for all the nodes here that is not in V, for example, N1 is not in V, N1 is reachable from a start node here, and all the paths meet at N3. If this is the case, we say that this if our V includes this start node and N3, then we say that V is weak control closure. However, for example, if our V includes, for example, node N3, node N2, and this start node, if this is the case, then we see that there exists paths from N3, from N1 to N3, and N1 to N2. These are two V paths because these paths end at a node in V, but at different nodes. If this is the case, then we say that this node N1 is weakly deciding, and whenever we have a weakly deciding node, that means V is not a weak control closure. And then to make V as a weak control closure, we include such nodes in the weak control closure of V. So that's the idea. So and this definition is why generalized, because for example, we do not need any notion of n node here. Even if the control flow graph does not have any n node, it will work in this case. Then another thing is, that I'd like to tell you is that when we consider weakly deciding vertex, there must exist two disjoint V paths here. If there exist two disjoint V paths, then we discover such weakly deciding vertex when we compute the weak control closure. However, this is the non-termination insensitive. Weak control closure captures non-termination insensitive control dependencies. A similar concept is a strong control closure, not similar, but a complementary concept that takes that is called non-termination sensitive control dependencies, in the sense that this definition considers non-termination of the program into account and captures control dependencies due to non-terminations. So this definition is the modification of the previous definition. We also require that for all control flow graph nodes n not in V, if n is reachable from V, so it must satisfy either of the two conditions. The first condition says that all V paths end at a unique node in V, like the weak control closure. But at the same time, we also need to meet this criteria, which says that all complete paths must include a node from V. That means if we start from, for example, N1, we see there is a non-terminating path. This is a complete path. And the strong control closure of V must include something here, either here, to take the non-termination into account. And but if another condition, the second condition says that either if there exists a non-terminating path, we include some node from the non-terminating path, or no V path exists from N. If this criteria is satisfied, then we say that V is a strongly control closed set. So these two definitions are non-termination insensitive and non-termination sensitive. They capture non-termination insensitive and non-termination sensitive control dependencies. So how do we apply these to program slicing? So usually program slicing is computed on the level of program dependency graph, and also it takes into account slicing criterion C. So C is a subset of control flow graph nodes. So in our case, we given any subset of control flow graph node C, we compute the slice set S here in a fixed point computation. So first we compute the subset S prime, which takes into account all the control flow graph nodes due to data dependencies. So this relation is here the transitive reflexive closure of data dependencies. And then once we get a subset S prime, then we compute the control closure relations here. This relation can be the weak control closure or a strong control closure depending on what is required by our client applications. So at the end, we check if this S double prime is equal to S or not. If they are equal, we reach a fixed point, we exit from this computation. Otherwise, we iterate this process again and again. So this way, at the end, since the control flow graph is finite, it will terminate, of course. And at the end, we get a subset S of control flow graph nodes, which is the slice of the program, depending on the slicing criterion C. So now if we think of this algorithm in terms of this program, for example, if our slicing criterion contains the statement 4, then what it will do is from 4 it checks the data dependency nodes into account, like statement 3 and statement 1, and then it computes the weak control closure or strong control closure and include this statement 2 into account. So at the end we get this slice, and then what's the application of this slice? For example, if we want to know, for example, a bug has surfaced at statement 4, and we want to know, okay, what are the other parts of the program that affects the computation here? We compute the slice and see what are the other parts of in the program that affect the computation here, and we can go and check whether any error is caused by other statements before statement 4. So this is one application of program slicing, or we can also apply it for information flow control to check if there is any information leakage or any security information leakage. I will give you an example later, or maybe now. So this is a Python function that I take from the CWE web page, saying that it has a timing leak. It basically validates a given password. Suppose once somebody types a password, it checks whether this password matches with the actual password or not. You see, first it checks the length of the two passwords, the actual password and the type password. If they do not match, the program terminates, exits from here. Otherwise, from statement 3 to 6 in a loop, it checks each character one after another. So we see that here is a difference of timing in the sense that if the password is different, the program, the actual password and the type of password are different, the program will terminate very quickly. So if an observer like here can observe the timing information, they know that this is not the actual length of the password. So they can try different password, right? And once they can, once an attacker can give the correct length of the password, then even inside this loop, if, for example, how many times this loop will iterate depends on how accurate the attacker gives the password. So a wrong password, giving a wrong password will terminate this program very quickly, and a more accurate password will take some time. So if an attacker can observe the time here probably, and if we assume that the attacker can try indefinite number of times, then it can reveal this actual password. Even though, I mean, in real life, the number of passwords that we give, number of try that we can apply is very limited. But I mean, we will have similar applications in many parts of the program. And for example, a malicious attacker can observe many different parts of the code and can reveal important information from the code. So just to understand how this timing behavior of the code varies, we can look into the control flow graph representation of this code and see that each node here, 1, 3, and 4, they are the control node. And if we assume that we have an attacker here, then the timing from 1 to end, or 3 to end, or 4 to end, I mean, it varies. So of course, I mean, we can capture this information, this timing information, by applying control dependency techniques. Another example is that, for example, a timing leak can lead to a cache attack or other kinds of attack. Here is another example. This is a very particular implementation of the advanced encryption standard algorithms. So in this code fragment, R1, R2, R3 are registers, and state is a map from public key to how is it called, secret key. And SBox is a constant array that spans over multiple memory blocks. So if and we assume that a very I mean, in this attack model, an attacker can observe the cache, for example. If this is the case, so, and since SBox spans over multiple memory blocks, so the value of R2 here in one iteration, I mean, decides whether this R3, the read of R3 should be from cache or from memory in another iterations. And because if we handle this cache into account, cache behavior into account, this is the very simple control flow graph of this program, and this is the cache aware control flow graph. At every point, like statement 2 or statement 3, we have here cache hit or cache miss. We can encode this into account here, and different cache behavior may lead to different timing, and based on different timing, the attacker can observe the cache. So if it can reveal R3 here, it can also reveal the R2, the secret key, by observing simply the timing, and when to observe the cache memory. So, we see that timing leaks can lead to other kinds of leaks, and in order to identify the timing leaks, we can apply a control dependency, provided that we extend it to time-sensitive control dependency. So the difference between a standard control dependency and time-sensitive control dependency is like this. Time-sensitive control dependency expresses not only whether X controls or decides the execution of Y, but it also says when. So I see I am running out of time, right, Ian?
Yes.
Yes. So yeah. So okay. Maybe just I tell very briefly about extension of this time-sensitive weak and time-sensitive strong control closures. And in this extension, it says that, for example, this definition is very similar to what we have seen before, the weak control closure, but we need one extra condition which says that all control flow graph nodes from N must end at a node in V, a unique node in V. But now we also require that they require equivalent execution time, and equivalent execution time must be according to some timing model I specified here, which I will omit now due to time limitations. And also we can extend this time sensitive strong control closures by including this timing information, saying that it requires equivalent execution time when all B paths met at a unique node. So this criteria, extra criteria, give us time sensitiveness. And this is the same program slicing algorithm. So once we compute the slice set S, and if there exists a node in S, for example, that is the source of secret input, then we can say that the program has a timing leak. So I'll not go into the details of this algorithm, how we compute this, but we have many contributions in this area. For example, in these two work, in SAS and in this Journal of Systems and Software, we have developed a very efficient algorithm to compute weak and strong control closures. And then in the third work here, we extend it to interprocedural programs. And in this work, we have computed this interprocedural WCC. And in the final work here that we submitted in SAS, that computes WCC incrementally. And if we look into the experimental results, we have developed all our algorithms in this Clang LLVM framework and performed experiments on SPEC CPU 2017. So we, on an average, we obtain a speed of 10x and 67x in computing WCC and SCC than the state-of-the-art method. And when we compute WCC incrementally, we obtain an average speed of 31x than the best baseline approach. And in case in case of computing interprocedural WCC, we improve the precision by 15%. So these are the summary of what we get in our previous work. So in conclusion, we can say that we improve the theoretical complexity by an order of magnitude, and not only theoretical complexity, we also improve practical efficiency and precision of our method. And time sensitive weak control closure, strong control closure, this is an ongoing work. I am still working on this topic, and I'm planning to submit it to a conference very soon in next month. And future work would be to develop time-sensitive WCC and SCC for interprocedural programs, and then apply them to analyze probabilistic programs. So that's the conclusion and future work, and I am open for collaboration. If anybody is interested to work in this or similar area, I will be very happy to collaborate. I think that's all from me.